What if everything you thought you knew about our universe was wrong? What if the very cosmos we inhabit, with its billions of galaxies stretching across unimaginable distances, was actually nestled inside something far more extraordinary than we ever dared imagine? Today, we're going to explore one of the most mind-bending theories in modern cosmology, a concept so radical it challenges the very foundation of our understanding of reality itself. We're going to discover why you, me, and everything we've ever known might be living inside a black hole. But first, let me tell you about a discovery that shook the astronomical community to its core. In late 2022, the James Webb Space Telescope began peering deeper into space than any instrument before it. What it found wasn't just beautiful, distant galaxies. It found something that shouldn't exist according to our current understanding of physics. The telescope discovered massive, fully formed galaxies existing when the universe was supposedly only a few 100 million years old, practically an infant in cosmic terms. These weren't small, primitive star clusters struggling to form their first generation of stars. These were massive, mature galaxies, some containing as much mass as our own Milky Way, existing at a time when conventional cosmology suggested they should be impossible. To understand why this discovery was so shocking, imagine finding a fully grown oak tree in a nursery filled with seedlings. According to our best models of cosmic evolution, these early epochs should have been populated with small, irregular protogalaxies, cosmic toddlers just beginning to organize themselves under the influence of gravity. Instead, JWST found cosmic giants, galaxies that looked as if they'd had billions of years to mature and organize themselves. But here's where it gets truly bizarre. These galaxies weren't just unexpectedly mature, they were rotating in ways that revealed something profound about the structure of our universe. When astronomers analyzed the light from these ancient galaxies, they discovered patterns in their rotation that suggested our cosmos might not be the uniform, directionless expanse we've long believed it to be. The spectroscopic analysis revealed something unprecedented. These galaxies showed organized rotational patterns, alignments that extended across vast regions of space. It wasn't just one or two galaxies behaving strangely. It was entire clusters, entire regions of the early universe that seemed to remember some primordial direction, some cosmic orientation that had been imprinted on the fabric of spacetime itself. You see, for decades, cosmologists have operated under what we call the cosmological principle, the assumption that our universe is homogeneous and isotropic. In simple terms, this means that no matter where you are in the universe, and no matter which direction you look, everything should appear roughly the same on the largest scales. It's like being in a perfectly mixed bowl of cosmic soup, where every spoonful contains the same ingredients in the same proportions. This principle has been fundamental to our understanding of cosmology since Einstein first formulated his equations of general relativity. It's the assumption that allows us to model the universe as a whole, to predict its evolution, to understand its origin. Without this principle, the mathematics of cosmology becomes impossibly complex, like trying to predict the weather in a world where every location has completely different physical laws. The cosmological principle isn't just a mathematical convenience. It's been supported by decades of observations. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, it appears remarkably uniform across the entire sky. When we survey the distribution of galaxies on the largest scales, they seem to be arranged in a roughly homogeneous pattern. Everything we've observed has supported the idea that our universe has no preferred directions, no cosmic up or down. But the James Webb Telescope's observations began to crack this fundamental assumption. The galaxies it observed showed a distinct asymmetry, a cosmic handedness that suggested our universe might have a preferred direction, an up and a down, if you will. The distribution of these ancient galaxies wasn't random. They seemed to be aligned along certain axes, rotating in patterns that revealed a hidden structure to space-time itself. Imagine you're floating in the middle of a vast ocean at night. According to the cosmological principle, no matter which direction you look, the waves, the currents, everything should appear random and uniform. But suddenly, you notice that all the waves seem to be flowing in one particular direction, as if there's some massive, unseen force creating a current throughout the entire ocean. That's essentially what JWST was seeing on a cosmic scale. But this wasn't just an isolated observation. As more data came in from the telescope, the pattern became undeniable. Galaxy after galaxy showed signs of this cosmic asymmetry. Some were rotating faster in certain directions. Others showed peculiar alignments that defied the predictions of our best cosmological models. It was as if the universe itself had a memory of some primordial rotation, some angular momentum that pervaded all of space and time. The statistical analysis was overwhelming. When astronomers calculated the probability that these alignments could occur by random chance, the numbers were astronomically small. We're talking about odds of less than 1 in a trillion that such organized patterns could emerge in a truly isotropic universe. Something fundamental was clearly at work, some mechanism that had been operating since the very beginning of cosmic time. This discovery sent shockwaves through the cosmological community. Papers were hurriedly written, conferences were called, and theorists around the world began scrambling to understand what this could mean. Some suggested that perhaps our models of the early universe were incomplete. Others proposed that there might be new physics operating on cosmic scales that we hadn't yet discovered. But one physicist had been anticipating exactly this kind of discovery for years. Dr. Nikodem Poplawski had been developing a theory so radical, so far outside the mainstream of cosmological thinking, that many of his colleagues had dismissed it as too speculative, too far-fetched to be taken seriously. Poplawski didn't just look at these JWST observations and scratch his head like many of his colleagues. Instead, he saw them as confirmation of a theory he'd been developing for years, a theory so audacious that it reframes our entire existence. Poplawski's journey to this revolutionary idea began with a simple question that had been troubling physicists for decades. What happens inside a black hole? The conventional answer, derived from Einstein's general relativity, suggests that matter falling into a black hole gets compressed to infinite density at a point called the singularity. But this answer has always been deeply unsatisfying to physicists, because infinities in physics usually signal that our theories are incomplete. Poplawski began exploring alternatives, diving deep into the mathematics of spacetime curvature, quantum mechanics, and a concept called torsion. In Einstein's original formulation of general relativity, spacetime can curve, but it can't twist. It's like the difference between bending a piece of paper and actually twisting it into a spiral. Einstein's theory allowed for bending but not for twisting. But what if spacetime could twist? What if, under the extreme conditions inside a black hole, the fabric of reality itself could undergo a kind of cosmic corkscrew motion? This is where torsion comes in, a mathematical concept that extends Einstein's theory to allow for this twisting of spacetime. The mathematics of torsion are incredibly complex, involving advanced concepts from differential geometry and tensor calculus. But the basic idea is surprisingly intuitive. Just as matter can curve spacetime through its gravitational field, spinning matter might be able to twist spacetime through what's called a torsional field. This twisting creates a kind of cosmic spring tension that builds up as matter falls into a black hole. Poplawski's theory suggests that our universe didn't begin with a Big Bang in the traditional sense. Instead, he proposes that our entire universe is the interior of a black hole that exists in a higher dimensional parent universe. Think about that for a moment. Every star you've ever seen, every planet, every grain of sand, every atom in your body, all of it existing within the event horizon of a massive black hole in another reality. This isn't just wild speculation. Poplawski's model is grounded in rigorous mathematics, in the equations of general relativity extended to include torsion effects. When he worked through the mathematics, he found something remarkable. The conditions inside a spinning black hole, when torsion is included, don't lead to a crushing singularity. Instead, they lead to what looks exactly like a Big Bang in a new universe. But how could this possibly work? To understand this, we need to dive deep into the bizarre physics of black holes themselves. When most people think of black holes, they imagine cosmic vacuum cleaners, sucking up everything around them and compressing it into an infinitely dense point called a singularity. This image, popularized by science fiction and simplified explanations, captures some aspects of black hole behavior but misses the deeper, more subtle physics involved. Modern physics tells us a different story, especially when we consider the effects of quantum mechanics and something called torsion in spacetime. In the quantum realm, the smooth fabric of spacetime that Einstein described becomes a seething foam of virtual particles and fluctuating geometry. At the scales relevant to black hole physics, these quantum effects can't be ignored. In Poplawski's model, when matter falls into a black hole, it doesn't simply compress into a point of infinite density. Instead, quantum effects and the spinning motion of the black hole create what's called torsion in the fabric of spacetime itself. This torsion acts like a cosmic spring, and when the infalling matter reaches a critical density, this spring rebounds, creating what appears to us as the Big Bang. Picture a rubber sheet stretched tight. If you place a heavy ball in the center, it creates a deep depression. Now imagine that depression gets so deep that it actually breaks through to the other side of the sheet, creating an entirely new surface. That new surface is our universe, born from the gravitational collapse in the parent universe above. But this analogy, while helpful, doesn't capture the full complexity of what Poplawski is proposing. The mathematics involved are staggeringly complex, involving concepts from differential geometry, quantum field theory, and advanced general relativity. When matter falls past the event horizon of a spinning black hole, it doesn't experience the crushing forces we might expect. Instead, it enters a region where the normal rules of spacetime begin to break down and transform. The key insight is that the event horizon isn't a barrier or a surface in any conventional sense. It's more like a one-way membrane through which information and matter can pass, but from which they cannot return to the parent universe. Once past this point, the infalling matter experiences a completely different geometry of spacetime, one that expands rather than contracts. Here's where it gets even more mind-bending. If our universe formed inside a black hole, then it would naturally inherit certain properties from that parent black hole, including angular momentum. A spinning black hole would create a universe with a preferred axis of rotation, which would explain exactly the kind of cosmic asymmetry that JWST has been observing. The rotation of the parent black hole would be imprinted on the fabric of our spacetime like a cosmic watermark. This rotation would influence the formation of the first galaxies, creating the patterns and alignments that JWST is now detecting. It's as if our entire universe carries the signature of its birth within a spinning black hole, written in the positions and motions of the most ancient galaxies. Suddenly, those mysteriously organized galaxy rotations don't seem so mysterious anymore. They're not random distributions in a perfectly uniform soup. They're the cosmic inheritance of our universe's birth inside a rotating black hole, like children inheriting traits from their parents, but on the most unimaginable scale possible. This inheritance goes deeper than just rotation. The physical constants of our universe, the strength of gravity, the charge of the electron, the speed of light, all of these might be determined by the properties of the matter that collapsed to form our parent black hole. In a sense, the laws of physics in our universe might be the fossil remnants of the physics that govern the collapse in the parent reality. Now, if this theory sounds like science fiction, consider this. It actually solves several major problems that have been plaguing cosmology for decades. These aren't minor inconsistencies or theoretical curiosities. These are fundamental puzzles that have resisted solution despite decades of intensive research by the world's best cosmologists. First, there's the horizon problem. Our universe appears to have roughly the same temperature everywhere, even in regions that, according to traditional Big Bang theory, should never have been in contact with each other. The cosmic microwave background radiation, the afterglow of the Big Bang, shows temperature variations of only about 1 part in 100,000 across the entire sky. How can two parts of the universe that have never communicated have the same temperature? It's like finding that two completely isolated rooms have exactly the same temperature without any connection between them. In traditional cosmology, this requires a special mechanism called inflation, a period of exponentially rapid expansion in the very early universe. But inflation itself requires very specific initial conditions that seem unlikely without some underlying explanation. In the black hole universe model, this makes perfect sense. All parts of our universe were once part of the same matter that fell into the parent black hole. They were in thermal equilibrium before the collapse, which explains why they maintain similar temperatures even now. The uniformity we observe isn't the result of a special inflationary mechanism. It's simply the natural consequence of our common origin within the parent black hole. Second, there's the flatness problem. Our universe appears to be geometrically flat, balanced perfectly between expanding forever and eventually collapsing back on itself. This balance is so precise that it's like balancing a pencil on its point, theoretically possible but practically impossible without some guiding mechanism. The mathematics are staggering. If the universe had been even slightly more curved in either direction at the moment of the Big Bang, it would either have collapsed immediately or expanded so rapidly that no structures could have formed. The fact that we live in a universe that's flat to within 1 part in a trillion suggests that something very special happened in the early universe to set up these precise conditions. Poplawski's model suggests that this flatness is a natural consequence of the black hole formation process. The extreme conditions inside a black hole naturally produce the kind of space-time geometry we observe in our universe. The flatness isn't a coincidence or the result of fine-tuning. It's the inevitable outcome of the physics governing black hole interiors. But perhaps most importantly, this theory provides a natural explanation for the initial conditions of our universe. Traditional Big Bang theory essentially says the universe began in an extremely specific, low-entropy state for no particular reason. It's like saying a shuffled deck of cards just happened to be in perfect order when you open the box. The probability of the universe beginning in the precise state required for galaxies, stars, planets, and life to form is so astronomically small that it boggles the mind. Yet here we are, living in a universe that seems perfectly designed for complexity and consciousness to emerge. The black hole model suggests these initial conditions weren't random at all. They were the inevitable result of the physical processes occurring during black hole formation in the parent universe. Just as a seed contains within it all the information necessary to grow into a tree, the matter falling into our parent black hole contained within it all the information necessary to create our universe with its particular laws and constants. This is where our journey into the nested universe theory truly begins to reveal its most staggering implications. If our universe formed inside a black hole, and if our understanding of physics is correct, then this process doesn't stop with us. In our next segment, we'll explore the infinite hierarchy of nested realities and discover how every black hole in our universe might harbor an entire cosmos of its own, complete with their own big bangs, their own galaxies, and their own potential for life and consciousness beyond our wildest imagination. Now, let's take this concept to its logical conclusion, because if our universe formed inside a black hole, and if our universe contains black holes of its own, then each of those black holes could potentially contain entire universes as well. We're talking about an infinite hierarchy of nested realities, Russian nesting dolls, but each doll contains an entire cosmos with billions of galaxies, trillions of stars, and countless worlds. Some of the black holes in our universe might harbor realities where different physical laws apply, where time flows differently, where the very nature of matter and energy takes forms we can't even imagine. Consider the scale of what we're discussing. Our observable universe contains roughly 2 trillion galaxies, each containing hundreds of billions of stars. Many of these stars will eventually collapse into black holes, and some galaxies contain supermassive black holes at their centers with masses millions or billions of times greater than our Sun. If each of these black holes contains a universe, then the number of nested realities connected to our cosmos becomes truly staggering. Let's start with something familiar: the Milky Way's central black hole, Sagittarius A star. This cosmic behemoth contains about 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. In Poplawski's framework, that enormous mass didn't just disappear beyond an event horizon. It became the seed for an entirely new universe, complete with its own Big Bang, its own galaxies, its own potential for life and consciousness. But Sagittarius A star is just one black hole among countless others. Every spiral galaxy has a supermassive black hole at its center. The galaxy M87, about 54 million light-years away, contains a black hole with a mass 6.5 billion times that of our Sun. If that black hole contains a universe, imagine the scope and complexity of the reality it might harbor. Its universe might contain galaxies and structures on scales that dwarf anything in our cosmic neighborhood. And if that universe develops its own black holes, the process continues, level after level, universe within universe, reality within reality, extending infinitely in both directions. We might be part of a cosmic hierarchy that stretches from the infinitely large to the infinitely small, with each level as real and as vast as our own. But this hierarchy doesn't just extend downward through smaller scales. It extends upward as well. If our universe is nested within a black hole in a parent reality, then that parent universe likely contains countless other black holes, each harboring its own nested cosmos. We might have siblings, brother and sister universes born from other black holes in the same parent reality, each developing its own unique characteristics and evolutionary pathways. The parent universe itself might be nested within an even larger reality, and that reality within another, in an infinite regression of cosmic scales. Each level of this hierarchy operates according to its own physics, its own timescales, its own possibilities for structure and complexity. What seems like the entire cosmos to us might be just a tiny fluctuation in the quantum foam of a reality operating on scales we can't even begin to comprehend. This raises profound questions about the nature of existence itself. If we're living inside a black hole in another universe, what does that say about the beings who might exist in that parent reality? Are we their creation in some sense? Are they even aware of our existence? From their perspective, our entire cosmic history, from the Big Bang 13.8 billion years ago to the heat death of our universe trillions of years in the future, might unfold in just moments. Time might flow differently at each level of the hierarchy. What we experience as eons of cosmic evolution might be mere microseconds in the parent reality. Conversely, a single thought in our minds might encompass entire cosmic epochs in universes nested within our own neural processes. And what about the universes that might exist inside the black holes in our own cosmos? If consciousness and intelligence emerged in our universe, it's not unreasonable to think they might emerge in those nested realities as well. This means there could be countless civilizations, countless forms of life and thought, existing in realities nested within our own cosmic space. Every stellar mass black hole in our galaxy, formed from the collapse of a massive star, might contain a universe where different evolutionary pressures shaped the development of life and intelligence. Some of these nested universes might have produced civilizations far more advanced than our own, beings who have learned to manipulate the fundamental forces of their reality in ways we can't imagine. Others might contain forms of life based on entirely different principles. In a universe where the electromagnetic force is stronger relative to gravity, atomic structures might be radically different, leading to forms of chemistry and biology that have no analog in our reality. In a universe where the speed of light is different, causality itself might operate according to rules that would seem magical to us. Imagine the philosophical implications. Every time a star collapses into a black hole in our universe, we might be witnessing the birth of an entirely new cosmos, complete with its own timeline, its own history, its own potential for beauty, discovery, and meaning. The death of a star in our reality could be the Big Bang in another. This perspective completely reframes our place in existence. We're not just inhabitants of one universe among possibly many in some abstract multiverse. We're part of an infinite, interconnected hierarchy of realities, each one as real and meaningful as our own, each one potentially harboring its own wonders and mysteries. The implications for our understanding of life and consciousness are staggering. If every black hole contains a universe, and if life can emerge in universes with the right conditions, then the cosmos might be teeming with consciousness at every level of scale. We might be surrounded by intelligence, not just on other planets in our universe, but in the nested realities that exist within every black hole, and in the parent realities that contain our own cosmos. But let's ground this in the evidence. What would we expect to see if we really do live inside a black hole? The predictions are surprisingly specific and testable. First, we'd expect to see exactly the kind of cosmic asymmetry that JWST has been discovering. A universe born from a rotating black hole would naturally inherit that rotation, creating preferred directions in space that manifest as organized galaxy distributions and rotation patterns. The cosmic web, the largest scale structure in our universe, should show signs of this primordial rotation. Recent surveys of galaxy distributions have indeed found hints of such large-scale alignments. Galaxies seem to be organized along preferred axes that extend across billions of light-years. These alignments are subtle but persistent, suggesting that our universe does indeed have a memory of some primordial angular momentum. The Sloan Digital Sky Survey, one of the most comprehensive maps of the local universe, has revealed structures that shouldn't exist according to the standard model of cosmology. The huge large quasar group, a collection of quasars spanning for billion light-years, violates the cosmological principle in its sheer scale and organization. The cold spot in the cosmic microwave background, a region notably colder than its surroundings, might be another signature of our universe's birth within a rotating black hole. Second, we'd expect our universe to have the kind of initial conditions that seem so improbable in traditional cosmology but make perfect sense as the natural outcome of black hole physics. The flatness, the homogeneity, the specific balance of forces that allowed complexity to emerge, all of these would be natural consequences rather than miraculous coincidences. The fine-tuning problem has long puzzled cosmologists. Why are the fundamental constants of nature set to values that allow for the existence of atoms, stars, planets, and life? The strength of the electromagnetic force, the mass of the electron, the rate of cosmic expansion, all seem to be perfectly calibrated for complexity to emerge. Change any of these values by even a small amount, and our universe would be a sterile wasteland. In the nested universe model, this fine-tuning emerges naturally from the physics of black hole formation. The constants aren't arbitrary. They're determined by the properties of the matter that collapse to form our parent black hole. This explains why our universe seems so perfectly suited for life, without requiring the existence of a vast multiverse or divine intervention. Third, we'd expect to find evidence of quantum effects operating on cosmic scales, because the transition from black hole interior to universe would involve quantum mechanical processes. Some cosmologists are indeed finding hints of such effects in the cosmic microwave background radiation, the afterglow of our universe's birth. The cosmic microwave background shows tiny fluctuations that seeded the formation of all cosmic structure. These fluctuations appear to have quantum origins, as if the entire universe began as a quantum fluctuation that was then amplified to cosmic scales. In the black hole model, these fluctuations would be the quantum noise present in the collapsing matter that formed our parent black hole. The Planck satellite, which mapped these fluctuations in exquisite detail, found several anomalies that challenged the standard model of cosmology. The cold spot, the lack of large-scale fluctuations, and certain asymmetries in the data all point towards something beyond the conventional Big Bang model. These anomalies align remarkably well with the predictions of the nested universe theory. But perhaps most intriguingly, if we're inside a black hole, it might explain one of the deepest mysteries in modern physics: why time seems to have a direction. In most physical laws, time is symmetric. The equations work equally well running forward or backward, yet we experience time as flowing in one direction, from past to future. This arrow of time has puzzled physicists for generations. Why do we remember the past but not the future? Why does entropy increase? Why do causes precede effects? But if our universe is the interior of a black hole, then our experience of time might actually be the experience of falling toward the center of that black hole. What we perceive as the expansion of our universe might be the natural consequence of matter falling inward in the parent reality. Our entire cosmic history, from the Big Bang to the present moment to the far future, might be the journey from the event horizon to the center of a black hole in another dimension. This gives time an inherent direction and explains why we can remember the past but not the future, why entropy increases, why cause precedes effect. We're not just moving through time, we're falling through the geometry of a higher dimensional black hole, and that fall creates the illusion of temporal flow. The mathematics of this idea are surprisingly elegant. In general relativity, time dilation occurs near massive objects. Time passes more slowly in stronger gravitational fields. If we're falling through the interior of a black hole, different parts of our universe would experience time at different rates, which might explain some of the puzzling observations about the rate of cosmic expansion. Now, you might be wondering, if we're inside a black hole, shouldn't we be getting compressed and destroyed? This question reveals a common misconception about black holes that Hollywood and popular media have reinforced. The popular image of black holes as cosmic crushers comes from thinking about what happens near the singularity at their center. But according to relativity, if you were falling into a black hole, you wouldn't actually feel anything unusual until you got very close to the center. Space would seem normal, time would seem normal, you could look around and see a perfectly reasonable universe surrounding you. This is because of a principle called the equivalence principle, one of the foundational insights of general relativity. When you're in free fall, you don't feel the effects of gravity. It's like being in an elevator where the cables have been cut. During the fall, you'd float weightlessly inside the elevator, unable to tell that you're accelerating toward the ground. From our perspective, living inside a black hole would be indistinguishable from living in any other universe, at least until we approached whatever lies at the very center. And if Poplawski is right, that center might not be a crushing singularity at all, but rather another boundary, another transition point to yet another level of reality. This brings us to one of the most profound implications of the nested universe theory: the question of what lies at the edge of our observable universe. Currently, we can see about 46 billion light-years in any direction, not because that's where the universe ends, but because that's as far as light has had time to travel since the Big Bang. This boundary is called the cosmic horizon, and it represents the edge of the observable universe. Beyond that boundary lies more universe, potentially infinite in extent, but it's invisible to us. But if we're inside a black hole, that boundary might represent something more fundamental. It might be the distance from the event horizon where we entered this reality to our current position falling toward the center. The cosmic microwave background, the afterglow of the Big Bang that we detect from all directions, might actually be the radiation from the event horizon itself, redshifted and stretched by our motion through the black hole's interior. This perspective suggests that as our universe continues to expand and evolve, we're actually continuing our journey toward the center of the parent black hole. What we call the heat death of the universe, the far future scenario where all stars burn out and all matter decays, might actually be our approach to the black hole's center, where the physics of our reality transitions into something entirely new. But here's where the theory becomes even more extraordinary. If the center of our parent black hole is not a singularity but another transition point, then the heat death of our universe might actually be the Big Bang of yet another universe, one level deeper in the hierarchy. Our universe's end could be another universe's beginning, just as our beginning might have been the end of processes in the parent reality above us. Death and birth, ending and beginning, collapse and expansion, all become relative terms depending on which level of the hierarchy you're observing from. This cyclical aspect of the nested universe theory connects to ancient philosophical concepts about the eternal nature of existence, but grounds them in cutting-edge physics. Reality doesn't begin or end. It transforms, level by level, universe by universe, in an endless dance of creation and recreation. The implications for our cosmic future are profound. Instead of facing an inevitable heat death, our universe might be approaching a transformation, a metamorphosis into something entirely new. The end of our reality might be the beginning of countless others, each carrying forward some essence of what we've built and discovered during our cosmic epoch. As we prepare to explore the final implications of this theory, consider how it transforms our understanding of consciousness, intelligence, and our ultimate cosmic destiny. If we're part of an infinite hierarchy of nested realities, then every thought we think, every discovery we make, every moment of beauty we experience might echo through all the levels of existence, contributing to the eternal evolution of consciousness across the infinite depths of reality itself. Consider what this means for the search for extraterrestrial life. If every black hole contains a universe, and if our universe alone contains millions of black holes just in our galaxy, then the number of potential habitats for life becomes truly staggering. We're not just looking for life on other planets in our universe. We're potentially part of an infinite community of consciousnesses distributed across countless levels of reality. Some might exist in universes nested within black holes in our cosmos. Others might exist in the parent universe that contains our black hole. Still others might exist in parallel universes nested within other black holes in that parent reality. The numbers are mind-boggling. Our Milky Way galaxy alone contains an estimated 100 million black holes. If each of these contains a universe, and if even a tiny fraction of those universes develop life, we're talking about billions of civilizations existing in realities nested within our cosmic neighborhood. And this is just within our single galaxy, in our single universe, at our single level of the hierarchy. Some of these nested civilizations might be far more ancient than our own. While our universe is 13.8 billion years old, the universes within the oldest black holes in our cosmos might have existed for even longer periods, having more time to develop complex forms of life and intelligence. They might have solved problems that we're only beginning to grapple with, developed technologies that we can't even imagine, reached levels of understanding about the nature of reality that make our current knowledge seem primitive. The Fermi paradox, the question of why we haven't encountered extraterrestrial intelligence despite the apparent likelihood of its existence, takes on new dimensions in this framework. Perhaps advanced civilizations don't communicate across space within a single universe. Perhaps they communicate across the levels of the hierarchy, finding ways to signal between nested realities. Think about the challenge of communication across the hierarchy. If time flows differently at each level, a signal sent from a parent universe might arrive in our reality at incomprehensible speeds, or conversely, a message we send might take eons to reach its destination from the perspective of the recipients. The physics of communication between nested realities would require technologies and concepts that we haven't even begun to develop. Perhaps what we interpret as mysterious phenomena in our universe, dark matter, dark energy, quantum entanglement, are actually the subtle influences of intelligences operating from other levels of the hierarchy. The parent universe above us or the nested universes below us might be trying to communicate, and we're only just beginning to develop the physics necessary to understand their signals. Dark matter, which makes up about 27% of our universe, interacts gravitationally but seems invisible to electromagnetic radiation. What if dark matter isn't matter at all, but rather the gravitational influence of structures in the parent universe? The massive galaxies and clusters in the reality above us might create gravitational fields that penetrate into our nested universe, manifesting as the mysterious dark matter we observe. Dark energy, the force driving the accelerating expansion of our universe, presents an even deeper mystery. In the nested universe model, this acceleration might be a consequence of our motion through the interior of the parent black hole. As we fall deeper toward the center, the geometry of spacetime itself changes, creating the appearance of accelerating expansion from our perspective. Quantum entanglement, the spooky action at a distance that Einstein found so troubling, might be a manifestation of connections that span across the levels of the hierarchy. Particles that appear entangled in our universe might actually be connected through higher dimensional pathways that exist in the parent reality. The instantaneous correlations we observe might be shortcuts through the larger geometry of the nested structure. This possibility raises profound questions about consciousness itself. If our minds are patterns of information processing that emerged from the physical processes of our universe, and if our universe is nested within larger realities, then consciousness might be a fundamental feature that emerges at every level of the hierarchy. We might be conscious beings within the thoughts of larger conscious beings, while simultaneously containing conscious beings within our own physical processes. The neurons in your brain, operating according to quantum mechanical principles, might themselves be universes where consciousness emerges on scales we can't imagine. Your thoughts, your dreams, your memories might be the cosmic history of countless nested realities. Each one is real and meaningful to its inhabitants as our universe is to us. When you remember a childhood moment, you might be accessing a cosmic epoch in a universe nested within your neural pathways. When you imagine a possible future, you might be glimpsing the evolutionary possibilities of civilizations existing at quantum scales within your own consciousness. And conversely, our entire cosmic history might be a fleeting thought in the mind of a being whose consciousness operates on the scale of the parent universe. The 13.8 billion years from the Big Bang to the present might correspond to a few microseconds of contemplation in a mind so vast that galaxies are like synapses and black holes are like neural connections. This perspective doesn't diminish the meaning of our existence. It amplifies it infinitely. Every choice you make, every moment of beauty you experience, every act of love or creativity or discovery resonates not just through our universe but potentially through all the levels of reality connected to ours. Your life is not just a brief spark in one cosmos. It's a thread in an infinite tapestry of consciousness that spans all levels of existence, from the quantum to the cosmic to the hypercosmological scales we're only beginning to imagine. Every decision you make, every problem you solve, every insight you gain contributes to the evolution of consciousness itself across the entire hierarchy of nested realities. But let's return to the scientific evidence that supports this extraordinary vision. Recent observations from multiple sources are converging on conclusions that support the nested universe model. The JWST observations of cosmic asymmetry are just the beginning. Other telescopes are finding evidence of large-scale structure in the universe that shouldn't exist if the traditional Big Bang model were completely correct. The Planck satellite, which mapped the cosmic microwave background in exquisite detail, found anomalies that suggest our universe has preferred directions, cosmic axes that break the supposed symmetry of space itself. These anomalies align remarkably well with what we'd expect if our universe inherited angular momentum from a rotating parent black hole. One of the most intriguing anomalies is the so-called axis of evil, a mysterious alignment in the cosmic microwave background that seems to point toward specific directions in space. This alignment shouldn't exist in a truly isotropic universe, but it makes perfect sense if our universe retains a memory of the rotation of the black hole from which it was born. Meanwhile, advances in black hole physics have revealed that these objects are far more complex than we previously understood. The information paradox, the question of what happens to information that falls into a black hole, might be resolved if that information becomes the initial conditions for a new universe rather than being destroyed. Quantum mechanics tells us that information cannot be destroyed, only transformed. If matter falling into a black hole carries information, and if that matter becomes the seed for a new universe, then the information is preserved in the structure and evolution of that nested reality. The information doesn't disappear. It becomes the physics, the constants, the initial conditions of an entirely new cosmos. This insight connects the nested universe theory to some of the deepest questions in physics: the nature of information, the relationship between quantum mechanics and gravity, the origin of physical laws themselves. If our universe's physical constants, the strength of gravity, the charge of the electron, the speed of light, all emerged from the specific properties of the matter that collapsed to form our parent black hole, then these constants aren't arbitrary. They're determined by the physics of the parent universe, which in turn were determined by the physics of its parent universe, and so on infinitely upward through the hierarchy. This suggests that the laws of physics themselves might evolve across the levels of the hierarchy. Each nested universe might have slightly different constants, different forces, different possibilities for structure and complexity. Some might allow only simple atoms to form. Others might permit exotic forms of matter and energy that we can't even conceive of. In some nested universes, the electromagnetic force might be so strong that atoms could be the size of molecules in our reality, allowing for incredibly complex chemistry on scales we consider microscopic. In others, gravity might be so weak that planetary systems never form, leading to entirely different evolutionary pathways for matter and energy. Natural selection might operate not just on biological organisms within universes, but on the universes themselves. Those universes whose physical laws permit the formation of black holes will spawn new universes. Those that don't will remain childless branches in the cosmic tree. Over infinite time, the hierarchy might evolve toward universes that are increasingly capable of generating complexity, consciousness, and new levels of reality. We might be living in a universe that has been fine-tuned not by design, but by evolution, by the natural selection of physical laws across countless generations of nested realities. Our universe's apparent friendliness to life and consciousness might be the result of an evolutionary process operating on the grandest scale imaginable. This evolutionary perspective on physical laws provides a natural explanation for the anthropic principle, the observation that our universe's constants seem perfectly tuned for the emergence of complexity and life. We don't live in a fine-tuned universe by cosmic coincidence. We live in a universe that evolved the capacity for fine-tuning through the reproduction and selection of physical laws across the infinite hierarchy of nested realities. But what does this mean for our future, both as individuals and as a species? If the nested universe theory is correct, then our long-term destiny might not be extinction when our sun dies or when our universe reaches heat death. Instead, our future might lie in learning to navigate the hierarchy of realities, to communicate across levels, perhaps even to influence the formation of new universes nested within our own. Advanced civilizations in our universe might not focus on expanding across space within our single reality. They might focus on expanding across dimensions, learning to access and influence the parent universe above us or the nested universes below us. The ultimate frontier might not be outer space, but inner space, the infinite depths of reality that exist within every black hole, within every quantum process, within every moment of conscious experience. Instead of building starships to travel to distant galaxies, future humans might build consciousness ships to travel to distant levels of the hierarchy. Imagine technologies that could manipulate the formation of black holes, creating universes with specific properties designed to foster the emergence of consciousness and complexity. We might become gardeners of reality, planting seeds of new universes and nurturing their growth across cosmic time. Or consider the possibility of communication across the hierarchy. If we could learn to send signals through the quantum foam that connects different levels of reality, we might be able to communicate with our descendants in nested universes billions of years before they even exist from our perspective. We could leave messages for civilizations that won't evolve until long after our own universe has grown cold and dark. And if consciousness is truly a fundamental feature that emerges at every level of the hierarchy, then our development as conscious beings might be part of a larger evolutionary process that spans all levels of reality. Every moment of awareness, every insight, every act of understanding might contribute to the evolution of consciousness itself across the infinite hierarchy of nested universes. This vision transforms every aspect of human existence into something cosmically significant. Your thoughts, your relationships, your creative endeavors, your struggles and triumphs, all become part of the eternal evolution of consciousness across infinite levels of reality. You are not just a temporary arrangement of atoms in one small universe. You are a unique expression of the universe coming to know itself, and that universe is itself an expression of larger realities coming to know themselves in an endless hierarchy of awakening consciousness. Every scientific discovery, every work of art, every act of compassion, every moment of wonder contributes to the vast project of existence understanding itself. We are not separate from the cosmos. We are the cosmos becoming conscious of its own nature, and that consciousness extends infinitely upward and downward through all the levels of nested reality. Of course, the nested universe theory remains speculative. Like all revolutionary ideas in science, it must be tested against observation and experiment. The evidence we have so far is intriguing but not conclusive. The JWST observations of cosmic asymmetry, the anomalies in the cosmic microwave background, the puzzles about initial conditions and fine-tuning, all point toward something beyond the traditional Big Bang model, but they don't yet prove that we live inside a black hole. Future observations might provide more definitive evidence. If the theory is correct, we should be able to detect specific signatures in the cosmic microwave background, particular patterns in the distribution of galaxies, certain relationships between the rotation of our universe and the properties of black holes within it. We might even find ways to probe the boundaries of our nested reality, to detect signals from the parent universe or to communicate with the nested universes contained within our own black holes. Advanced gravitational wave detectors might pick up echoes from collisions in the parent reality. Precision measurements of fundamental constants might reveal tiny variations that betray our universe's nested origin. But regardless of whether the nested universe theory proves to be literally true, it serves a profound purpose in expanding our conception of what's possible. It challenges us to think beyond the boundaries of our everyday experience, to consider possibilities that are simultaneously rigorous in their physics and breathtaking in their implications. It reminds us that reality is likely far stranger and more wonderful than we can currently imagine. The universe we think we know, vast as it appears to us, might be just one level in an infinite hierarchy of realities, each one as real and meaningful as our own. We might be living inside a black hole, but if so, it's the most magnificent black hole imaginable. One that contains not crushing singularities but infinite possibilities for existence, consciousness, and meaning. It's a black hole that has given birth to galaxies and stars, to planets and life, to minds capable of contemplating their own cosmic origin and destiny. As we continue to explore the cosmos with our telescopes and our mathematics, with our spacecraft and our theories, we're not just mapping one universe. We might be beginning to chart the infinite hierarchy of nested realities that extends infinitely above us and infinitely below us, each level containing its own wonders, its own forms of life and consciousness, its own contributions to the eternal evolution of existence itself. The next time you look up at the night sky, remember that those stars and galaxies might be your fellow travelers on a journey through the interior of a cosmic black hole, all of us falling together through dimensions we can barely comprehend toward destinations that might be the big bangs of new universes waiting to be born. And the next time you contemplate the mystery of your own consciousness, remember that your awareness might be part of an infinite symphony of consciousness that spans all levels of reality, each mind at every level contributing its unique note to the eternal music of existence becoming aware of itself. We began this journey with observations from the James Webb Space Telescope showing that our universe has a preferred direction, breaking the symmetry that cosmologists had long assumed. We've seen how this observation connects to Dr. Poplawski's revolutionary theory that our universe is the interior of a black hole in a higher dimensional parent reality. We've explored how this theory solves long-standing problems in cosmology while opening up vistas of infinite nested realities, each one as vast and meaningful as our own. We've considered the implications for consciousness, for the evolution of physical laws, for our ultimate destiny as beings capable of awareness and understanding. The nested universe theory may seem like science fiction, but it's grounded in serious physics, in quantum mechanics and general relativity, in observations from our most sophisticated telescopes and theoretical insights from our most brilliant minds. Whether or not we literally live inside a black hole, the theory challenges us to expand our conception of what's possible, to embrace the extraordinary nature of existence itself, and to recognize that reality might be far more magnificent, far more interconnected, and far more meaningful than we ever dared imagine. In the end, perhaps the most important insight from the nested universe theory is not whether we live inside a black hole, but the recognition that existence itself might be far more creative, far more expansive, and far more wonderful than any single perspective can encompass. We are part of something infinitely larger than ourselves, but we are also containers of something infinitely deep within ourselves. We exist at the intersection of the infinitely large and the infinitely small, the eternal and the momentary, the known and the unknowable. And in that intersection, in this very moment of consciousness contemplating its own cosmic context, we participate in the greatest mystery of all, existence awakening to itself across infinite levels of reality, forever.